Hello everyone, welcome to my channel Quality Talks. In this series of video, we will discuss about correlation and regression. In real manufacturing processes, whenever a problem occurs, engineers and quality professionals must identify which factors are responsible for the variation in output. Let us understand this using a practical case study. In our case, Mr. Problem Solver is working on improving fuel injection flow consistency. The flow rate of fuel injection is the critical output characteristics, and variation in this parameter can affect engine performance and fuel efficiency. After brainstorming and process analysis, the team identified three possible input variables that may influence the flow rate. One is injection pressure, second is nozzle diameter, and third is fuel temperature. Now the important question is, which input variable has the strongest relationship with flow rate? And another question, do these input variables actually influence the output at all? Now the answer lies here in correlation analysis. To solve this problem, engineers need a method to measure the relationship between input variables and the output. Correlation analysis is a statistical technique used to determine whether two variables are related and how strongly they move together. For example, in our case study, we want to examine the relationship between injection pressure and flow rate, nozzle diameter and flow rate, fuel temperature and flow rate. In real life, we also know some of the input variable those affect the output variable, like more the study hours input X resulted into the higher exam marks output Y. Higher the ambient temperature input X resulted in higher ice cream sale output Y. Higher the speed of the vehicle input variable resulted in higher braking distance output Y. Now the question is, how do we measure the strength of this relationship? The answer is correlation coefficient. The correlation coefficient, represented by the symbol R, is a statistical measure that indicates both the strength and direction of the relationship between two variables. This is the formula for correlation coefficient. The value of R varies between -1 to +1. If the value of R is close to +1, it indicates a strong positive relationship. Positive correlation means when X is increasing, Y is also increasing. If the value of R is close to -1, it indicates a strong negative correlationship. Negative correlation means when X is increasing, Y is decreasing. And there could be a situation where there would be no relationship between two variables. For different value of correlation coefficient, we can determine the type of relationship. If the correlation coefficient lies between +0.90 to +1, then it is a very strong positive correlation. 0.70 to 0.89, it is a strong positive correlation. 0.40 to 0.69, it is moderate positive correlation. 0.20 to +0.39, it is a weak correlation. 0 to 0.19, very weak or no correlation. 0, definitely no correlation. Similar in the negative side. So negative side -0.90 to -1 is very strong negative correlation. -0.70 to -0.89, strong negative correlations. So in this way, by calculating correlation coefficient R between two variables, we can identify the relationship between two variables. In our case study, to identify the relationship between flow rate and injection pressure, nozzle diameter and fuel temperature, Mr. Problem Solver collected the output flow rate at different value of input. This is the table where data is collected. Now we will explain how to calculate correlation coefficient using MS Excel. We have put the data into MS Excel. These are the input X, injection pressure P, nozzle diameter D, fuel temperature T, and output flow rate Fr. With different value of input, output is measured. Now we want to see the relationship between input and output. First simple formula is equal to CORREL. This is correlation formula in Excel. So in this formula, we have to put two variables data, like our first input variable is this injection pressure. So we will select 72, all the readings we have. Okay, then put comma, it is asking for array 2. So this is the second data, output data we have, and we will put all the data. In this way, correlation coefficient is calculated as 0.79. Now this is one method, but we need to identify the correlation of output with these three input variables. So we want to do it in one go. So how to do it in one go? Very easy. Just go to data and data analysis. You will find correlation here. Okay. Select the data. We have all these data with us. Okay, and data is grouped in columns. We have label in first row. So these names like injection pressure, nozzle diameter, these are the labels. Output range we want here in our sheet only here. Okay, so just put OK. So we can find out this table. This table is directly flow rate and injection pressure. Correlation coefficient is 0.7911. Flow rate and nozzle diameter, the correlation coefficient is 0.824 and 0.264 with fuel temperature. Okay, let's put it into the presentation. So with the help of Excel, we have calculated the correlation coefficient. Okay, we will summarize it. Our output flow rate and inputs are three parameters. Correlation coefficient with injection pressure is 0.79. That shows strong positive correlation. With nozzle diameter, correlation coefficient is 0.82. That is also a strong positive correlation. With fuel temperature, it is 0.26. It's a weak positive correlation. Now the question comes, how much of the variation in the output is explained by the input variables? We know there is a relationship and a strong positive relationship. But how much output is explained by the input variable, that we want to know. We can get our answer by coefficient of determination. Coefficient of determination R square represents the percentage of variation in the response variable. Response variable is the output variable that is explained by the predictor variable, that is input variable. Okay. So it's simple. When you square the correlation coefficients, it becomes coefficient of determination. The value of coefficient of determination R square varies from 0 to 1. In our case, we have already calculated the correlation coefficient. So coefficient of determination we will directly get by squaring it. So coefficient of determination for injection pressure is 0.624. That means 62.4% of variation in flow rate is explained by injection pressure. Similarly, coefficient of determination for nozzle diameter is 0.672. That means 67.2% of variation in flow rate is explained by nozzle diameter. Fuel temperature, coefficient of determination is 0.068. So only 6.8% of variation in flow rate is explained by fuel temperature. Now the critical question came, can we develop a mathematical model to predict flow rate using injection pressures and other parameters? So the answer is yes, by using regression analysis. We will discuss regression analysis in next video. So please stay connected. Please subscribe my channel for such more videos, and please give me your feedback on these videos. Thank you very much.